everyone. Today we're going over the exam practice session number 5. The first question is about probabilities. So there are a bunch of problems that ask you to manipulate the rules of probability that you've learned in order to find equalities. So just to go over, the most important rules that you'll use in this problem are that so the law of total probability, so that's the sum over A of the probability of your variable equals all of its options is equal to 1. Bayes' rule, which is that the probability of A given B is equal to the probability of A and B divided by the probability of B. The chain rule, which is the probability of A and B and C can be decomposed into probability of A given B and C times the probability of B given C times the probability of C. And these are the main rules that are useful for the beginning. So now here we're trying to find, for the part A, we're trying to find which which of these expressions sum to 1. So for the first option, this looks very similar to our law of total probability, except that we have a conditional on B. Turns out the conditional on B doesn't matter. This is equal to 1 because you're just saying you're giving me a particular value of B, and then asking to sum over all the possibilities of A, the probability of A given that particular value of B. And since we need there to always, A will always have some value with this particular value of B. So if we sum up all the ways that A can have different values, then those will sum to 1. The second part, this one's easiest to understand if you make a table to see what you're doing. So we have the B and A and the probability of A given B. So B can have values of 0 and 1, A can have values of 0 and 1, and we know from the first option that the sum over all possible A's for A given B has to equal 1. So if this is 0.25, then the next option has to be 0.75. And maybe if B is 1, then we have a 0.1 and a 0.9. And the second option is saying, well, what if we summed for a particular value of A, like A equals 0, what if we summed up these two numbers? So this would give us 0.35. And this doesn't mean anything. Or similarly, for if A equals 1, what if we summed up 0.75 plus 0.9? This is a number greater than 1, so it definitely can't be a probability, and it definitely isn't 1, so not this option. Okay, what about the next one? The next one we have the joint probability of A and B, and we're summing over A and B. So this is like if we made a new random variable C that was just equal to the tuple A comma B. And its possible values would be A1 and B1, or A1 and B2, etc. And so in this expression here, we're summing over, this is equivalent to summing over all the possible C values of the probability of C, which we know is equal to 1 from the law of total probability. Okay, here we have a conditional on B, and we're summing over the values of A and B. So thinking back to our table that we had earlier, it's like summing all of these values up. But we already know that summing over just A would give us 1. So if we flip the order of the sum, which you can do because sum is commutative and associative, then we would have the sum over little a of p equals a given b equals b. And this is 1 for a particular b. And then we're summing over b. So this is 1, this whole expression is equal to 1 times the size of the domain of b, which is not necessarily 1. In the next option, we are summing over the product of p of a and p of b. So here, since p of a is not it has no b in it, we can take it out of the inner sum. So we can sum over a of p of big A equals little a, multiplied by the sum of b over b equals b. And we know this is equal to 1. And 1 times, so that means that this is equal to the sum over a of p of a equals a, which equals 1. I'm running out of space, but the next problem is only summing over a. So this is equal to, we can take the b out because it's not dependent on a. The probability of b equals b times the sum over a of p of big A equals little a. This is 1. So this is equal to p of b, which is not 1. And obviously it's not none of the above, since we have found some valid expressions. In the next problem, we're trying to find expressions that are equivalent to the joint of a, b, and c. This first option, this is the chain rule. This is exactly the definition of the chain rule. So that's good. And the second option, you might be tempted to say, well, we could multiply the p of a to get rid of that conditional and the p of b to get rid of this conditional. But this is not true, because p of a times p of b is not guaranteed to equal p of the joint of a and b. In the third option, this is, again, the chain rule. So if we multiply, so we have probability A and B conditional on C times probability of C. So by the chain rule, we know this is A comma B comma C. Again, we just use the chain rule in its definition to get that this is the joint. And here, we almost have the chain rule, but we're missing the extra C in this expression. So this is not equivalent to A and B and C. And the third one, this is nowhere near being the joint of A, B, and C. Okay, now we are trying to find A given B and C. From Bayes' rule that P of A given B and C is equal to P of ABC divided by BC. In the first option, we have P of ABC on the top, that's good. And on the bottom, we're summing out A. So the bottom is equal to P of B and C. So this checks out. In the second option, we have the chain rule. On top gives us P of ABC. And the bottom is P of BC. Great. Here, we can multiply the top and bottom each by P of C. So that here we get the chain rule on the top to get P of A and B and C. And on the bottom, the chain rule gives us P of B and C, which is, again, what we want. Now, for this option, we can also try, this looks like the chain rule on top, so we can try multiplying by P of C on the top and bottom again, which gives us what we want on top, A, B, and C. But the problem is that the denominator now has an extra probability of C. So this is equal to A given B and C, but divided by P of C. So not great. In the second option, we have the correct thing on the bottom, but the numerator is missing a P of A and needs to do some extra rearranging. So we're not going to get a P of A on the top. And for the last one, this is just you could try multiplying by P of C on the top, but then you have to multiply on the bottom too. So we get the right thing on top, A and B and C. But in the numerator, since we have this condition on A, we can't get only B and C on the bottom. For part D, we're now given that A is independent of B given C. So as a reminder, that means that P of A given C times P of B given C equals P of A and B given C. It also means that P of A given both B and C is equal to P of A given only C, since it's independent of B as long as C is around. And we're trying to find expressions that are equal to probability of A given B, which, as we know from Bayes' rule, is equal to probability of A and B divided by the probability of B. For the first option, we have probability of B on the bottom, which is good. The top is equal to probability of A and B given C. So we're not going to be able to lose this C here in order to get the expression we actually want. In the second option, we get probability of A and B given C on top, and probability of B given C on the bottom, which means that we're almost there, but the problem is that there's these probabilities of C here that are getting in the way. Third option, we're summing out C's. So this looks pretty promising because we're going to be able to get rid of the C's at the end, but we can use them to manipulate A and B in ways where they're independent. So the numerator of the expression is equal to summing over C of the probability of A and B given C times the probability of C. So this means that it's just equal to the probability of A and B and C by the chain rule. And on the bottom, we've got the sum over C prime of probability of B and C equals C prime, again using the chain rule. Now when we sum over C in a joint distribution, that means we can just take it out. So this is equal to the probability of A and B divided by the probability of B, which is exactly what we want. Now in this option, we have a probability of A given B and C on the top and a probability of A given C on the bottom, which is nowhere near and not at all going to get to an A and B on top and a B on the bottom. So this is not the correct option. For the fifth option, we have B given A and C times probability of A and C. So we can chain rule this to be the probability of B and A and C equals C on the top. And on the bottom we have a probability of B. Since we're summing over C, this is just equal to the probability of A and B. Order doesn't matter between objects in a joint distribution. So probability of A and B divided by probability of B, which is what we want. And for the last option, we have probability of A and B on the top, but probability of A and B on the bottom. So this is equal to 1, which is not correct. And for the last part E, we're given that A is independent of B and given C, but also that just A is independent of C. So A independent of C means that A given C equals probability of A. So that's going to be pretty useful. So, and we want to find expressions that are equivalent to the joint of A and B and C. This option would be correct if B were independent of C, but this is not given. So we can't say this is true. For the second part, we know that probability of A equals probability of A given C. And since A is independent of B given C, this is also equal to probability of A given B and C. And so according to the chain rule, this is going to be equal to probability of A and B and C. For the third option, we can chain rule this into probability of B and C. And this term, just as in the previous part, is equal to probability of A and B and C. So we get A and B and C as the product using the chain rule. To simplify this, we can see this is probability of A, and that this is probability of B given C, and that this is probability of C given B, which is not equal to the probability of A given B given C. Oh, sorry, the probability of A and B and C. Here, this is basically the same as the third option on the previous page. Probability of A given C equals probability of A given B and C. And this chain rules into probability of B and C. So together we get probability of A and B and C. And on the last option, we're missing probability of C. Okay, so the second problem is on variable elimination. We start with this base net given here, and we know that we have observed C, and we're trying to figure out the probability of the joint distribution of A and E given this evidence of plus C. This problem walks us through the variable elimination in order to find this query. So we're given these factors, and we're trying to eliminate D. In order to do that, we find all the factors that have a D in them, and to make a factor of 2 that's going to have some inputs and is equal to the sum over all the possible values of D of the product of the factors that have D's. So in this case, that's E given D, F given D, and F1 of A plus C and D. Notice that I'm using little d's instead of big D's because they're particular values of d that we're summing over. So the inputs to factor 2 are then all the remaining variables that are used in this computation. So we've got e, we've got f, and we've got a, and plus c. So the factors that we have left are all the ones that we didn't use last time. So p of a, p of plus c, p of g given plus c and f, and then our new factor, f2 of e, f, a, and plus c. Now we want to eliminate g, so we get f3 of some inputs is equal to the sum over the values of g of all the factors that contain g. So that's only one of them, so we've got p of g given plus c and f. So the inputs to f3 are plus c and f, and the factors that remain are the ones we didn't use. So again, p of a, p of plus c, f2 of e, f, a, and plus c, and then our new factor f3 plus c and f. So notice that eliminating g didn't reduce the number of factors, but it means that we no longer have to take the distributions of g into account, and we can we have fewer variables to deal with, even if we have the same number of factors. Now I want to eliminate f, so again we had factor 4 of some inputs is equal to the sum over the values of f of all the factors that include f. So that's f2 and f3. f2 of e, little f, a, plus c, times f3 of plus c and little f. So the inputs to f4 are e, a, plus c, and that's it. So the factors we have left are, again, p of a, p of c, and only f4. Now we want a formula to compute our query, the probability of a and e given plus c. Because of the rules of Bayes-Nets and variable elimination, we know that probability of a and e given plus c is proportional to the product of the remaining factors. However, we need this distribution to sum to 1 because we're given a particular value of c, so we're only looking at one thing to condition on, and then we need the joint of a and e to sum to 1 to be a real probability. So in order to do that, we can just take our unnormalized probability and normalize it by summing over a and e of p of a, p of plus c, and f4. Now we need to figure out which of the factors is the largest factor. So the size of the factor is equal to the size of each variable, which in this case is 2, times the number of the number of variables that are uninstantiated. So for factor 1, we have 2 uninstantiated variables. So factor 1 has size 2 to the 2, which is 4. Factor 2 has 3 uninstantiated variables. So the size of factor 2 is 2 to the 3, which is 8. Factor 3 is only 1 variable, so that's size 2. And factor 4 has 2 variables again, so this is size 4. So it means that the largest factor was factor 2, which has a size 8. Now for the last part of this question, we need to find an ordering for the variable elimination such that the size of the largest factor is minimized. So we want to never have large factors because large factors require a lot more computation. In this case, if we go back to our BayesNet, the reason factor 2 is so large is because we eliminated D very early on. And D has a lot of connections. And for each connection a variable has, that's an extra table that's going to be joined into the factor. So in order to minimize your larger factors, you want to first pick variables that are that have a small number of connections. So in the solution, we start with B, which is fine because the factor we'll get from that is the sum over B of P of B, P of little b given A times P of D given little b, which is a factor that only involves A and D. So that's size 4, so we're good. Now we can eliminate G, and if we eliminate G, we get a factor that only involves one uninstantiated variable. So we'll get sum over G of P of little g given plus C, and G given F. So this is a factor that only has size 2, since it's F is the only uninstantiated variable. Next we can eliminate F, which should give us the sum over F of P of F given D and factor 2 of plus C and little f, which again is a factor that only has size 2 since C doesn't count. And finally we can eliminate our last variable D, and hopefully we have small enough factor. So we're going to sum over D of the probability of D given plus C times the factor 3 of D and plus C times the factor 1 of A and D. And this this factor then only has, and the probability of E given D. So this factor then only takes A and E and plus C as input. So this factor is also size 4. And so we've limited our the size of the maximum factor to be 4 or fewer. Thanks for watching.